This is a nice opportunity to tell you about some recent work. This is not a survey talk like many have talked about. This is a joint work with Matthew Anderson, who was a postdoc with me for a couple of years in Cambridge. This paper I'm going to tell you about, well, short version appeared in Stacks 2014. There's a longer, well, somewhat longer version on the archive, and which we're in the process of revising at the moment. But, I mean, the results I'll tell you a little bit about maybe in the second half of the talk. In the first half, I'm going to try and give you a little bit of context and a little bit of motivation for why we're looking at this. And I mean, in some sense, this is work originating, you know, in the area of finite model theory, descriptive complexity, and I want to try and tie it in and motivate it from the point of view of circuits. Okay, so I mean, I assume most of this audience is quite familiar with the setup of circuit complexity, but just for setting the baseline, I'll run through some basic definitions, right? So we have a language, L. So in the alphabet 0, 1, we think of this as a family of Boolean functions, one for each length n. So each function fn takes strings of length n and gives us a 0, 1 value, okay, which corresponds to whether that particular string is in the language or not. Now, we think of the function, the Boolean function, as being evaluated by a circuit. I'm not going to define what a circuit is. Well, it's a directed acyclic graph. The gates are labeled by Boolean operators. I will consider other operators in a minute. The inputs, that is the sources of our directed acyclic graph with no incoming edges, are labeled by variables x1 to xn, and there's a distinguished gate determining the output. And obviously, the function fn computed by the circuit is given by assigning these values to the variables and then looking what the value of the output is. Okay, this is all, I assume, entirely unsurprising. If we put a size bound on the circuits and require that the circuit Cn is bounded in size by a polynomial in n, the class of languages which admit such a family is what we call p/poly, non-uniform polynomial time. If, in addition, we put the requirement that the function which takes n to the circuit Cn is itself computable in polynomial time, we get a characterization of the class P, right? Now, it's, I think, fairly clear that for these, for these definitions of these complexity classes, it doesn't really matter whether we restrict ourselves to the Boolean basis or any other complete basis of gates, as long as the individual functions given by the gates are themselves polynomial time computable. So throwing in threshold gates, majority gates, doesn't make a difference. Of course, it makes a difference if you restrict your circuit family in various ways, such as, you know, to constant depth and so on, but not in the general case. Okay. Now, of course, the conjecture, if you will, the ultimate goal, I think, of the field is, you know, we believe, let's say, that NP is not contained even in p/poly. We're far away from being able to prove anything like this, but what we can prove is NP is not in some restricted circuit classes by putting some kind of restrictions on the circuits. I mean, I'm going to just, I should say, I'm going to mention 3 results. This is a sort of random personal selection. I know there's a lot more lower bound results out there. We know parity, for instance, is not computable by any constant depth polynomial size family of circuits. This goes back to 1983, first accepts, I suppose I should say ITI as well independently. So putting a restriction on the depth of the circuit, we get a unconditional lower bound. But obviously, it's not just NP. I mean, it's a function of very low complexity, so that just shows the model is rather weak. I'll mention Rasborov's result from '85 that no monotone polynomial size families of circuits decides clique. Of course, the point is that clique is itself a monotone function. I mean, it's given by a family of monotone functions. So in principle, there's a monotone family of circuits, but they're necessarily big. They grow super polynomial. Okay, I also mentioned this because I like the result. Ben Rossman shows again, for constant depth families of circuits of size clique, lower bound of size n to the k over 4, which is tight. Okay? Right. So the point is, monotonicity, constant depth are ways of restricting the family of circuits so that we can actually prove lower bounds. And I say this mainly because I'm going to introduce another notion, kind of restricted form of circuits, which I call symmetric circuits, and essentially define, if you will, just like with the monotonicity thing, there's class of functions which are, the functions are naturally symmetric. I say this with a caveat. I know symmetric functions, Boolean functions has another meaning, so I'm going to use the word invariant for the Boolean functions. So the functions have certain symmetries which, if you impose on the circuits, we can prove lower bounds. That's where we're going with this. Okay. So that's constant depth. Once we throw in majority gates onto constant depth circuits, we actually have no separation, no known separation from NP, even though this seems like a very weak circuit model. Okay. So that's sort of the background from circuit complexity, which I suppose many of you, I know many of you know more about this than I do. So to motivate the notion of symmetry I'm going to introduce, I'm going to talk about circuits for graph properties, right? So say the language we're trying to decide is a property of graphs, like, is a graph three-colorable, is a graph connected, something like that. So the input is going to be a string which encodes the graph, right? So in particular, we think of it. Now I'm going to write Cn for a circuit which works on n vertex graphs. So now n is not the number of Boolean inputs to the circuit. The circuit Cn will take n squared inputs, which we think of as the potential edges of the graph. In other words, for each pair ij in the set 1 to n, we have an input labeled ij, which can be 0 or 1 depending upon whether there's an edge, that edge is present or absent in the n vertex graph. Okay? It's just enumerate the adjacency matrix as a string is all we're doing. Okay? And of course we define, the polynomial time graph properties are exactly given by such families of circuits where the size is bounded by a polynomial and the family is uniform. So in the sense I defined, the function that takes n to Cn is in P. We can replace P by something much weaker without changing the family. This is also well known. So I'm just going to talk about P time uniform in this talk. You can assume you can weaken the uniformity condition to d log time if you like. Okay. Now, what's the symmetry condition? So I'll call a circuit invariant. Now I say Cn is invariant, but really this is a condition on the Boolean function computed by Cn. If it's invariant, if you take any input graph and you permute the vertices of the graph, the output should be unchanged. Okay? This is not the same as saying that the Boolean function is symmetric in the sense we say, because we're not allowing an arbitrary permutation of the inputs, right? We're only allowing permutations corresponding to permutations of the vertices, which means though there are n squared inputs, the permutations we consider are generated by permutations of n. Okay? Here it is spelled out in particular. So an input is a graph, which we can think of as a function from n squared to 0, 1. And you pick a permutation in Sn, then the circuit should accept the input g if and only if it accepts the permuted version of g, which is one where on input ij is the same as g on the inputs pi I, pi j. So you have to apply the same permutation to both coordinates. That's what makes it different from symmetric Boolean functions. Now, of course, any property of graphs, which is reasonably a property of graphs rather than the particular presentation, will satisfy this. So, the kinds of things we're really interested in deciding about graphs, I've just picked, 4 random decision problems on graphs: connectivity, perfect matching, Hamiltonicity, three-colorability. They're all invariant in this sense. And so I say it's more general than symmetric ones, because symmetric ones the symmetric Boolean functions in the graph context will be just those which tell you something about the number of edges, right? Some property of the cardinality of the edge set. And this is far more general. Okay, so that's what I mean by, I will use the word invariant for this property. I will use the word symmetric. Now this is a property of circuits rather than of the function, to mean the following, which is something which guarantees invariance, and that is a circuit is symmetric. If you take any permutation of n and apply it to the inputs, it can be extended to an automorphism of the whole circuit. So in other words, for every permutation of n, there is an automorphism of Cn. This is now an automorphism of thinking of the circuit as a directed acyclic graph. And it's a permutation of the gates, which preserves all the preserves the connectivity, preserves the labeling of the gates, and all of that. So that's what I'll call by a symmetric circuit. So here it is. For every permutation of Sn, there's an automorphism of C, and in particular takes the input ij to pi I pi j, okay, and extends to the whole circuit. It's clear that any symmetric circuit is invariant because, maybe I should have said, in particular, I will require the automorphism to fix the output gate, right? So the output gate is unchanged, and then then it follows that any symmetric circuit is invariant. But the converse is false, okay? There are invariant circuits which are not symmetric. I mean, just take natural polynomial size circuit for deciding parity. How would you do it? I mean, parity of, okay, so I have n inputs. I mean, I will, right? Take my circuit for parity. This is an invariant, I mean, in the context of graphs, this is saying that the number of edges in the graph is even. Or odd, whichever way you, yes. And clearly it's not symmetric because x1 and x2 are connected by this gate, but x1 and x, so the permutation that swaps x2 and x3 will, there's nothing, it can't be extended to taking this gate to anything because there's no gate for x1 and x3. You can take any invariant circuit like this and convert it to a symmetric one, just by, as it were, taking its closure under all the permutations Sn. Right? In other words, for any permutation which isn't an automorphism, you just add the new gates, which would be images of these under that permutation, and create it. And because it's invariant, that doesn't change the function computed. So any invariant can be converted to a symmetric one, but that's potentially exponential in size. And my first claim is, in this context for this one, that's actually necessary. We'll see. Okay? If you convert this into a symmetric circuit, not only do you get the exponential size, there is no polynomial size circuit symmetric circuit that will do this. Okay. So why are we interested in symmetric circuits? So now I'll give you the motivation where we arrived at this, which, as I said, comes from finite model theory. So take first order logic. We'll start with a simple case. We think of the logic as a way of specifying properties of graphs, right? So here's a sort of formal definition of the syntax of first order logic, which I'm not going to run through for you. But so this is in the language of graphs. Maybe I should have said this caveat right at the beginning. I'm saying everything about graphs because it's clear to describe the model. You can fix any finite relational signature and the same sorts of things apply, right? This is more general, but I'll stick to talking about graphs. So in the language of graphs, first order formulas are atomic formulas which say there's an edge between x and y. We have the Boolean operations. We have quantification over the vertices of the graph. You can think of a formula without free variables. In other words, a sentence of the logic defines a property of the graphs. Here I've just written down a first order formula that fits on one line. It says that the graph has an independent set of size 3, right? There are 3 vertices that are pairwise distinct. And I suppose strictly speaking, in my atomic formulas, I should have also had equalities, x equals y. But three vertices which are pairwise distinct and pairwise non-adjacent. So this is an independent set of size 3. Okay. Now you can convert any such formula into a family of circuits in a standard way. What do you get, right? So here's the standard translation spelled out for you. You start with the formula. You take any subformula, which will now have some free variables, x. I mean, phi is a sentence without free variables, but a subformula will have free variables. And you consider any assignment of values to those free variables. Now, the values are vertices of your graph, right? And for each such assignment, you have a gate in your circuit. Now, if your formula psi x bar is of the form, let's say there exists y theta, then the gate, which is labeled by psi, let's say a bar, I'll put square brackets around this, will be a disjunction, large disjunction over all the gates, theta a bar, let's say a bar 1, theta a bar 2, etc., up to theta a bar n. Okay? And I'll show you this existential case and say, now simple induction on the structure of the formula gives you your circuit for a fixed size n. Okay. What can we say about the circuit that we get? Well, first of all, it's of constant depth. That's given by the depth of the formula, right? It's a polynomial size. What's the size bound? It is some constant c. Well, c is the number of subformulas of phi, times n to the k, where k is the maximum number of free variables in any subformula of phi, right? That's just by the construction I gave you. And third, it is symmetric, because if you have a permutation of n, it extends to an automorphism of the whole circuit by the action which takes the gate labeled psi a to the gate labeled psi pi a. You apply the permutation pi to the particular instances that actually appear in here, and that gives you a gate to map to, and that you can easily check that is an automorphism of the whole circuit, and it, as I said, extends the given permutation. So we get symmetric polynomial size constant depth circuits from first order logic. Now, in the context of descriptive complexity, we've studied extensions of first order logic, like fixed point logic, in an attempt to get closer to polynomial time. So if you haven't seen this before, I'm not going to give you a full-fledged definition. But fixed point logic is, you get by adding to first order logic a sort of form for inductive definitions. I'll illustrate with an example. So this is a sentence of fixed point logic that defines connected graphs, which is a property that's not first order definable. So what does this say? So remember, E is the edge relation on graphs. T is a new relational variable. So think of this formula. It says x equals y, or there is some z with an edge from x to z, and zy is in the relation t. T is an undefined relation. This construction, LFP txy, basically says take the least fixed point of the equation t equals this inside thing over here. So the smallest such relation is in fact the reflexive transitive closure of the edge relation. And then those things say that every pair UV is in that reflexive transitive closure, which is to say the graph is connected, right? So this is a mechanism for having inductive definitions. We throw it into the logic. What can we say now? Old theorem, going back more than 30 years now, independently proved by Emmerman and Vardy, is that if you restrict yourself to structures where the vertices are a linear order, so we have a linear order on the elements which we can use in here, then everything in polynomial time is expressible. The other direction that everything you can express as polynomial time is actually much easier. But here I just want to note, of course, putting this order requirement is a way of killing all the symmetries in your input. And in particular, it allows you to write down formulas which are not graph properties at all, like there is an edge between the first vertex and the third vertex, which, depending upon which order you present the graph in, may be true or false, right? So that's why this is, as I said, if we're interested in sort of preserving the symmetries of the problem, this is overkill. In the absence of order, we know that fixed point formulas, well, we can do connectivity, we can do p-complete problems like the circuit value problem, but we can't say that the graph has an even number of vertices, or the graph has an even number of edges. These are undefinable, and this is known by sort of fairly simple, at least now we think of them as simple Ehrenfeucht-Froissart game arguments. Meaning? Well, exactly. I'll say a little bit more. You don't have to sort of go to second order. We'll see in a moment. So what's the relationship between fixed point logic and circuits? I told you, how to go from first order formulas to circuits. If you start with a fixed point formula and you fix the size of your input to be n, then you can actually unfold that induction and get rid of the inductive definition altogether, and you get a first order formula, which is equivalent to phi. It's just the unfolding gives you a quantifier depth, a depth of the formula, which is a function of n. It's a polynomial in n generally, okay? so we get a first order formula phi n, which is equivalent to phi on all graphs with at most n vertices. Right? Bounding the number basically means bounds the depth of your induction. You can unfold it into a first order formula. So the depth becomes now a polynomial in n, but we can still bound the number of free variables that occur in each subformula by a constant k. This requires a slightly clever argument in unfolding the induction, but you can keep this bound to a constant, which means that when you then do the translation to the circuits that I described, you get polynomial size circuits, and they're still symmetric by exactly the argument we had before. So every formula in FP is given by polynomial size symmetric circuits. Okay. Here's just a little note. I mean, the inexpressibility results for evenness I mentioned before. If you actually look at the proofs, they actually prove something slightly stronger. They're not about fixed points. They prove that any even non-uniform family of first order formulas, as long as it uses a constant number of variables, cannot express evenness. So it's this constant bound that really is crucial to the arguments. Okay. So we can translate these formulas to symmetric circuits. Now, I told you before that I was going to show you that this can't be done by symmetric circuits. Of course, that doesn't follow from this, right? I mean, we only have the translation. In fact, even number of vertices is not definable in fixed point logic, but that's clearly given by a symmetric family of circuits. You just need the one gate circuit for each n, which is true if n is even and false if n is odd, right? So evenness of the number of vertices is clearly doable by symmetric circuits, but not by fixed point logic. But even number of edges is not doable by fixed point logic, and I will argue it's not doable even by polynomial size symmetric circuits at all, okay? Right. Now we go, and this is getting to your question in some sense. Given that you can't count in fixed point logic, it was proposed to add a mechanism for counting. This was also goes back to Immerman in the early 80s. Who defined this logic, which we call fixed point with counting. I'll denote it FPC. And he actually proposed that this might be sufficient to express all polynomial time properties. This turned out to be false, but I want to say there's still a lot of interesting things to be said about FPC. So again, let's not worry too much about the formal definition. The logic has two sorts of variables. We have the variables which range over, well, the domain of the structure, if you will, the vertices of the graph, just like we had before. And we have variables which range over numbers in a limited range, from 0 up to the size, from 0 up to n, let's say, right? And what links the two is that when you have a formula with a free variable x, we can write this thing over here, which basically says that this number, right? So nu is a variable which ranges over numbers. This number is the number of x that satisfy phi. Okay? And in addition, I mean, on the numbers, we have an order, so we can do arithmetic and we can do, various things we'd like to do with numbers. Okay. That's fixed point logic with counting. I'm not going to use the sort of formal definition. I'm never going to be writing formulas explicitly, so you don't have to worry about the syntax or semantics. The main idea is it introduces a mechanism for counting by having these sort of separate numbers, a number domain on the side. And it's now fairly easy in this to say things like the number of vertices is even, or even the number of edges is even. It's possible to do this in the logic. Okay. Now, we want to translate this back. I mean, again, what we want to do is like what we did for fixed point logic, fix the size and translate it into a first order formula. And the best way to describe this is by considering an extension of first order logic where we allow quantifiers of the form, there exists I elements x such that phi for any constant I. Right? For every constant I, we have such a quantifier. And this is to be read as there are at least I distinct elements x for which phi is true. Now this is not adding to the expressive power of first order logic because you can always expand it out into I different quantifiers. But we're going to combine it by restricting the number of variables to a fixed number x1 to xk to give us ck. Note that expanding this into I different quantifiers would blow up the number of variables. So this is a fragment of first order logic, but not a fragment of first order logic with a constant number of variables. Okay, we call this ck. Well, yeah, I just said this. Now we can show that if you start with a sentence of FPC, there is actually a constant k, so that it translates into a family of ck formulas, right? One for each size of input n. Okay. Again, you unfold the definitions, the inductive definitions, and then you replace those counting terms you have in FPC by sort of Boolean combinations of these counting quantifiers, which you can do once the size of the structure n is fixed. Okay. So what do we get? We get that any property expressible in FPC is given by a polynomial size family of symmetric circuits with counting gates. Okay? So in other words, we can again get the translation into symmetric circuits, but we have to allow counting gates to basically incorporate these quantifiers. Okay? If we don't have counting gates, we don't have this constant bound k on the number of variables, and so we don't have a polynomial size bound on the size of the circuit. Okay? So to keep the symmetry when we translate FPC, we have to allow counting gates or threshold gates, majority gates, any one of those would do. Okay? So now, this thing, in other words, I've already hinted, well, I've told you, though not proved to you, that this thing cannot be converted into a symmetric polynomial size circuit with Boolean gates alone. But it follows from this that this can be expressed by a polynomial size symmetric family of circuits with counting gates. So adding counting gates actually strictly increases the power of polynomial size symmetric circuits. Okay? And I mean, in some sense, to be the case with counting is the more interesting one. Now, the reason why it's more interesting is because the expressive power of FPC is far more interesting than the expressive power of FP. Immerman proposed that FPC might actually capture all polynomial time properties because anything that turns out to be obviously polynomial time, you can pretty much express in FPC. The natural constructs that are used in polynomial time algorithms have a natural translation into FPC. And I say this includes things like CVP, two-colorability, two-set. All of these are actually already in fixed-point logic. Things which are not in fixed-point logic but still in FPC, well, there's this monumental result by Martin Grohe relatively recently where he showed that any proper minor closed class, well, on any proper minor closed class of graphs, any polynomial time property can be expressed in FPC. I say this is a monumental result. It's not yet published in full form. The proof is available in a 500-page manuscript that appears on Martin Grohe's website. It's due to appear, I assume, still under refereeing, but as a AMS monograph. It's sort of a culmination of a decade of work along these lines, but it gives us a really wide range of things which are, it's still surprising that they're in polynomial time, but they're actually expressible in FPC. Okay. I sort of hesitate to mention my own results in the same breath, but in a recent paper with Matt Anderson and Bjarke Holm, we showed that you can express linear programming problems in FPC. Essentially, this is a translation of the ellipsoid method into fixed point formulas. And then the ellipsoid method being powerful enough that it doesn't have to be confined to linear programs you can give explicitly as long as you can define a separation oracle. And we use this to show, for instance, that maximum matching, or I should say, the size of a maximum matching in a graph is definable by an FPC formula. This resolved an open question that, in fact, refuted, I should say, a conjecture that Blas-Gorevich and Shelah had posed in about 98. So FPC is quite powerful. It can express lots of interesting things. On the other hand, we know it's not all of polynomial time. There are limitations already back, I say 1982, that's the journal version, but probably in about 89, Cypher and Emmerman showed that there are polynomial time properties of graphs that are not definable in FPC. Okay, so it is not all of polynomial time. And other inexpressibility results followed. Either, some explained, some obtained as a consequence of this, but others, by adapting their techniques. I'll mention a few. We can prove, now this is unconditionally, this is not, assuming P is different from NP, this is trivially true because FPC is a fragment of P, but we can prove unconditionally that, say, Hamiltonian cycle and satisfiability are not definable in FPC. What do I mean? Hamiltonian cycle is a graph problem. What do I mean by satisfiability? I would take the formulation that Ian gave in his talk, namely, you have a set of clauses, a set of variables, and relations which say this variable appears positively in the clause, this variable appears negatively in the clause. That'll do. And as Ian mentioned, these things are known to be NP complete even under first order reductions without the assumption of an order on the input. And then this result immediately follows. Because FPC is closed under first order reductions. If there were an FPC, all of NP would be an FPC, but we know it's not. Okay. Three-colorability is not definable in FPC. This is something I was able to prove. Three-colorability is not NP complete under first order reductions, provably not NP complete. So this doesn't follow by the argument I gave above, but it is actually proved by a construction which adapts the actual graph construction they use. More recently, we got, I think, what we call a natural polynomial time problem. This one didn't look natural to us. Solvability of systems of linear equations. We do it over any fixed finite abelian group. In particular, you can take the two-element group, in which case this is just XOR SAT, is not definable in FPC. Okay?
But you did linear programming in FPC on the previous slide, and now you're saying linear systems of equations you can't do.
This is over a finite field.
Oh,
Right?
okay.
Over the rationals, we can do it. Right? In fact, again, just like with FP, these lower bounds are proved by showing that any non-uniform, even a non-uniform family of CK formulas cannot define these problems, right? So it's this crucially this bound K, this constant bound on the number of variables, which is used in these proofs. Okay. I'm half an hour into the talk, and that was sort of the background. The main results that we prove are, in some sense, I gave you the translation from formulas to circuits, which is easy. Our main results are going the other way. We translate circuits into formulas. If you just restrict yourself to Boolean circuits, no threshold gates, we show that any polynomial-sized uniform family of circuits can be expressed by an fixed point formula. You may say there's a contradiction there because I said evenness of number of vertices is given. But you have to interpret the fixed point formula not in just the graph, but in this structure, which is the disjoint union of the graph with a linear order of size n. So now in this, it's easy in fixed point logic to say that the number of vertices is even because you just have to say this linear order has even length, which is easy. But it's impossible to say that the number of edges is even because there's nothing that connects this graph to this order. So effectively, your fixed point logic is working over an unordered graph where we know you can't do that. So it requires an argument. You just do an explicit game argument on such structures, and you can prove that the number of edges is not definable. And by this theorem, then the number of edges, as I said, this is not given by any polynomial size family of circuits, family of symmetric circuits. If you throw in threshold gates, things become cleaner because you don't need this linear order on the size because in fixed point with counting, it comes for free. You have this number domain, right? So it's available for free. So there's an exact characterization. Class of graphs is accepted by a uniform polynomial-sized symmetric family of threshold circuits if and only if it's definable in FPC. So FPC has a now characterization as a class of symmetric circuits. Okay. So now I want to tell you a little bit about the proof of this, maybe in 15 minutes. So one direction is easy, as we've seen, translating formulas to circuits. In the other direction, it's really, we're given a family of symmetric circuits, and we sort of analyze the kinds of, okay, sorry, before I get into the proof, I have one slide about consequences. So we get a circuit-based characterization of FPC definability, and obviously, some consequences are inexpressibility results for these logic. Now, we can think of them as circuit lower bounds. So there's no polynomial size family of symmetric circuits deciding if an n-vertex graph has an even number of edges. That was this thing I mentioned here. You can't translate threshold circuits of polynomial size to symmetric polynomial size circuits without a blow up. That's because this thing is doable with threshold circuits, symmetric circuits. And invariant circuits can't be translated into symmetric circuits, even if you allow threshold gates in the symmetric circuits with only polynomial blow up. And that's the Seyfert-Immermann result. There are polynomial time properties of graphs which are not in fixed point with counting. Okay, so now I'll tell you a little bit about the proof. So the proof, we're given these circuits, and we want to translate them into formulas. And our main tool is really just, if you will, a combinatorial analysis of the automorphism groups that can appear in polynomial size symmetric circuits. So first of all, we can assume without loss of generality that the automorphism group of the circuit is actually Sn acting in the natural way. Two reasons for this. One, as long as every element of the input appears as an input gate, then Sn must appear as a subgroup of the automorphism group. It must be embedded as a subgroup of the automorphism group. That's just by the definition of symmetry. So that's one direction. In the other direction, we want to make sure that there are no other automorphisms which, as it were, fix all the inputs but move other gates around. But you can show easy inductive argument that you can eliminate such things by merging gates. I mean, you must have gates doing exactly the same thing. So you just merge them, okay? So from now on, we just assume that our circuits, the automorphism group is exactly Sn and acting in the natural way on the inputs. Key notion is the notion of a support. So say we have a gate in the circuit. The stabilizer group of the gate is simply the subgroup of Sn of those permutations which fix the gate G. Okay? We say that a subset of n supports the gate if the following is true. Okay, the pointwise stabilizer of the set X is simply those permutations which fix every element of X. And this is a support of G if everything in this pointwise stabilizer is in the stabilizer of G. In other words, if you fix every element of X by your permutation, then you fix G. Right? G is not going to move under your automorphism. Now, note that when we gave the translation from logic into circuits, every gate actually has a small support, namely those elements that appear in here. Because once you fix all of these, you're fixed. I mean, the action of the permutation pi was to take this to pi a. If pi is constant on everything in A, it fixes this gate. So the circuits we get from formulas have the property that there is a constant k, so that every gate has a supportive size at most k. And our main technical construction is showing that this is actually necessary. Once you've fixed the fact that your circuit is symmetric and polynomial size, you have to have constant size support. Okay? So the way we do this is we introduce the notion of a supporting partition. I mean, I say introduce. I mean, I'm not an expert on permutation groups, but I fished around in the literature and didn't find exactly this. So we kind of defined it and proved a few simple properties of this. What do I mean by supporting partition? Say you have a permutation group G. Then a partition of N, we say supports G, if whenever you take any permutation that fixes each part individually, set-wise, it is in G. Okay? Now, it's an easy lemma to show that for any group G, there is a coarsest partition that supports it. And that's simply because if you have two partitions, P and P prime, that support it, you can take the finest partition that's coarser than both P and P prime and show that any permutation that fixes each part of this can be expressed as a composition of permutations that fix each part of P and each part of P prime. Each one fixes one or the other. And since all of those are in G, the composition is in G, and therefore you have this. That, hand wavy, that's all there is to it. There's a coarsest partition that supports G. Okay, so I'll write SPG for the coarsest partition that supports a group G. And I'm going to be interested in two things, the pointwise stabilizer and the setwise stabilizer of this partition. Pointwise stabilizer, I mean those permutations that fix each part of this partition setwise, and the setwise stabilizer, those that fix the partition but may move the parts around. Okay, in other words, if you will, these are the ones for which the corresponding equivalence relation is invariant under these permutations. Okay, now we can show that G is sandwiched between these two groups. Okay? This is, for most groups G, this is not very informative. I'll just give you an example. Suppose G was the alternating group on n elements. Then the coarsest partition that supports it is simply the partition into singletons, in which case this is the trivial group containing just the identity, and this is the full symmetric group, right? So it tells you nothing in that case. But in the cases we're interested in, this turns out to be actually very informative. So, okay, why is this true? The first inclusion is by definition. I said the second follows from the fact that if you have any permutation pi, its action on this partition is to, you take its image of this partition under this permutation, and you can show that that's the coarsest partition supporting the conjugate group. And it's a sort of simple calculation then to show that this follows. Now we know that the orbit of any gate in C under the action of the automorphisms, right? So the is given by this, right? It's the size of the symmetric group divided by the size of the stabilizer of G. Okay, this is just the orbit stabilizer theorem. So what we're going to do is we're going to get an upper bound. Sorry, we want to get an upper bound on the stabilizer because that gives us a lower bound on the size of G. Or conversely, if we know that the orbit of G is bounded because we're in a polynomial size circuit, that gives us a lower bound on the size of the stabilizer, and we're going to use that to extract bounds on the size of the supporting partition. Okay? So here I'll give you now the main technical statement. It's more technical than we need because we prove it not just for polynomial size, we prove it for sub-exponential size. Right? We show that all gates have small support. What does small mean? Okay, so we prove it for essentially anything up to size about 2 to the n to the 1/3. Right? So epsilon is somewhere between 2/3 and 1/3. As long as your circuit is bounded by that, right? And n is big enough, this is just some constant bound, then every gate has a support of size at most log s over log n. So in particular, if s is polynomial, this is a constant. Okay? And we do get this by bounding supporting partitions of the stabilizer groups of gates. So yeah, the main corollary we're interested in, polynomial size symmetric circuits, there's a constant bound on the support of every gate. Proof of the support theorem, I'll give you a quick sketch. This, as I said, it's mainly the combinatorics of permutation groups. There are 3 parts to it. So we fix a permutation group whose index in the symmetric group is bounded by S, which, as I said, if this is the stabilizer group of a gate, it's bounded by the size of the orbit of the gate, and therefore by the size of the circuit. And we claim that if this is the case, then you look at the number of parts in the coarsest supporting partition, it's either small, very small, or very big. Okay? In other words, either K is bounded, but the number of parts is bounded by this, or n minus the number of parts is bounded by this. Okay, and I'm not going to give you this. This is just you literally write down how many permutations there are if you have a partition of K parts which fixes each of the parts, and then you do a fairly loose upper estimate. You get this. Okay. And as I said, we use the bound S, the 2 to the n to the 1/3 that we had on the previous slide. Okay, I'll move over this. Okay, so the supporting partition is either small, has a small number of parts, or a large number of parts. Secondly, we prove that if it has a small number of parts, then there is one enormous part, which has most of n in it. This is a much more delicate combinatorial calculation, so I'm not going to tell you. Well, again, we kind of derive that if you have fewer than this parts, in other words, the partition is small, and each of them is bounded by this, you can actually show that the number of permutations that fixes all of the parts is just too small. So the stabilizer group is too small, so the orbit of the gate must be big. As I said, it's a bit more delicate calculation. But all of this so far has nothing to do with circuits. It's purely combinatorics of permutation groups. Okay, so what have we proved? The number of parts is either small or big. And if it's small, then there's a big part. And now we rule out the possibility of the number of parts being big. And this is where we use the sort of circuit structure. We show that because it's sort of by induction on the directed acyclic graph structure. You start with the leaves, where you know the number of parts is small because the inputs are labeled with just 2 elements, so there's a support of size 2, and any permutation that moves everything else fixes this. And then you show that if there is a gate whose supporting partition has a large number of parts, all of whose inputs the supporting partition has a small number of parts, we can then construct automorphisms that move these sort of gates independently, forcing the orbit of this gate to be large, which gives us a contradiction. Okay, so that's the inductive argument. Okay, now, so what do we have? Now we know that in a symmetric circuit, every gate has a supporting partition which has one enormous part. Therefore, the union of all the other parts is a support, in the sense we said. If you fix all of those, you fix the partition, therefore you're in the stabilizer group of the gate. And that's our support theorem. Okay? Right. So now we have, in a polynomial size circuit, every gate has a constant size support. What do we do with this to translate into the logic? Well, let's say we have a gate. We'll write SPG for this small support. And now we're given a polynomial time function that generates symmetric circuits. That's the assumption. And we want to get out of this a formula of fixed point logic. Well, you can write down a formula which, interpreted just on a linear order, will define the structure Cn. This is simply because on ordered structures, you can do all of polynomial time inside FP. And we can show that the support of each gate is computable in polynomial time, so also definable in FP on this bit. Now, you're given an input structure A, say a graph. If you have say you assign, a mapping of the structure onto the inputs of your circuit, right? Then whether a particular gate evaluates to true or false depends only on what this assignment does on the support of G and on nothing else. So we can associate with each gate a relation on A, which defines effectively it's a succinct encoding of those assignments which make that gate true. And we show that this thing is definable by induction, that is by a fixed point, on the structure of the circuit. Okay? And now this inductive definition can be turned into a formula of FP if the circuit has only and, or, and not gates, or FPC if it has threshold gates. So we needed this thing on the side, which, as I said, that's why in our theorem, it's fixed point logic on graphs with this linear order on the side. But when we're in fixed point with counting, we don't need it because it's available for free as the domain of numbers. Okay, and so we get, in the case of threshold circuits, we get FPC categorically. Okay, that's what I'm going to say about the proof. Okay, I was finishing at 10 to? Well, I'm done actually. So let me just say, now, I mean, the main thrust of this is that I think fixed point with counting has a natural characterization in terms of circuits, right? FPC is the same as those properties decidable by symmetric polynomial size threshold circuits. Sorry, that's not a proper subset of FPC. That should be proper subset of P, right? But FPC, we know, from its study in finite model theory, we know, as I said, things that it can express and things that it cannot. There are interesting upper and lower bounds for it. which we can now think of as circuit lower bounds for this, what I think is a fairly natural class of circuits for graph properties. And so I'll tell you, none of these are new results, but I'm just stating them now as upper and lower bounds for circuits, which I think makes this class of circuits possibly an interesting object of study. And note, these lower bounds are all unconditional lower bounds. They're not, no complexity theoretic assumptions here. So circuit value problem is definable, SAT is not. Okay? Two colorability is definable, three colorability is not. Right? This is even in, I mean, both of these are even in fixed point logic, but those are not in categorically, unconditionally not in fixed point with counting. Two SAT is definable, three SAT is not. Perfect matching is definable, Hamiltonian cycle is not, right? Again, unconditionally. This is, I mean, these are sort of relatively easy to see. This requires quite some work to establish. Linear programming, as I said, is doable. In fact, we can do systems of equations over the rationals, but XOR SAT is not, right? We can't solve systems of equations over two-element field. So this is, as you'll see, I mean, I had a list of NP-complete problems. Here's my first one in P, appearing on the lower bound side. Graph isomorphism, I think, is an interesting one. On planar graphs, in fact, on any minor closed class of graphs, by Martin-Grohe's result, is in here. On bounded degree graphs, it's provably not, right, in fixed point with counting. So there's something more going on over here. I mean, I think, I mean, now there's many things you can do over here, right? Of course, you can add more gates. I mean, why stop at counting? You can pull XOR SAT over here by adding a suitable gate for, which defines a sort of invariant Boolean function, say, which gives you the rank of the adjacency matrix of G in the two-element field. Add that as a gate, and you pull over XOR SAT, you get symmetric polynomial-sized circuits. But then, of course, you lose all the lower bounds for these. As far as we know, we don't have lower bounds against that family of circuits with the rank gate. But I think, I mean, from the point of view of what we do in finite model theory, I think this shows that in terms of getting for a logic for P, a characterization of all the invariant polynomial time properties, I think you have to find a logic that breaks the symmetry barrier in some sense, because I think it's a sort of this suggests that's a hard barrier. I mean, I said lower bounds. I didn't say what the lower bounds are. You can extract. Certainly super polynomial bounds. You can extract from what we know. I mean, for each of these, I think you can probably, in terms of formulas of CK, there's probably linear lower bounds you can get on the number of variables. You can pull it back through our proof of the support theorem to get an actual bound on the size of the circuit, but, sorry, well, never mind, I'm not going to bother. To get an actual bound on but the limitation there is in our support theorem, we have this 2 to the n to the 1/3, above which our proof doesn't work. So you won't get bounds big, higher than that. But I think you can probably get something like that for most of those problems. But anyway, I think mainly I want to advertise this as a potential circuit model, which I hope people would be interested in. I'll stop there.
So, Anuj, you're using your symmetric circuit model to prove lower bounds. So there's a nice analogy. What if one tried to take this to the arithmetic circuit world? Consider the permanent. There's a natural sense in which the permanent is a symmetric polynomial in the sense that basically it's just if we think of the permanent as the monomials represent perfect matchings in a complete bipartite graph, then the symmetries are the obvious thing. So it's an invariant polynomial, and we can naturally define the same notion of symmetric circuits in the arithmetic world. Do we know an exponential or superpolynomial lower bound for symmetric arithmetic circuits doing the permanent?
Okay. I mean, I should say, so my co-author, Matt Anderson, has a follow-up to this addressing exactly that question. But I wouldn't swear to standing up here and remembering exactly what the result is. But all I know is, I mean, he gets a lower bound of some kind, but he says it's not better than what can be derived by other methods. So he wasn't very excited by what he got out of this.
Well, what other methods? I mean, in other words, is there a method for proving the symmetric arithmetic circuit lower bounds?
Yeah. Okay. I don't. I'd be trying to recall things he told me, on a blackboard a year ago, and I wouldn't. I hesitate to try and do this. But yeah, he has a follow-up which isn't fully written up, addressing exactly the question of the polynomials for the permanent. Symmetric polynomials. I think he had to put some other restrictions. There was symmetric polynomials, which were sums of like I said, I don't want to try and recall this on the fly.
Any other questions? Thanks, Anuj, again.